Okay, we will start then. This is a week 6 of the TA session of Design of Steel Structures taught by Professor Damodar Maiti. I am Trisha Chakravorty, one of the course teaching assistants of this course. I am a PhD student at the Indian Institute of Science, Bangalore. I will start with a brief recap of the previous 5 weeks. In the first week, we looked at why at all we are studying this course, design of steel structures. Now there are two broad branches of structural engineering: analysis and design. Analysis is a forward problem. In analysis, we are given the structural dimensions, the boundary conditions, and applied loads, and we have to find the response of the structure in terms of forces, stresses, deflections, and strains. And design is the inverse problem. Here we are given the loads that has to be withstood by the structure and some criteria on maximum deflection. So these the loads to be withstood by the structure are called the collapse limit state, and the criterion on maximum deflection are called the serviceability limit states. And then we have to find the optimum size of the structural elements. We have to take a call about what materials we are going to use, what is the grade of steel or concrete, and what the dimensions and the arrangement should be. Now, steel versus concrete. Steel and concrete are the most commonly used structural materials, and concrete is the most versatile material for construction. The one that is used in all residential buildings, most of the ones we see around us. So, why steel? Steel is much stronger than conventional concrete. That is, its compressive tensile strengths are higher. It has a high strength to weight ratio, so steel structures are lightweight, and steel is ductile compared to concrete. So steel undergoes a lot of deformation before it actually breaks, unlike concrete that undergoes brittle failure. So steel failure of steel structures gives ample warning time, which is very important. And however, steel is much costlier than concrete, so we do not usually go for steel in uh, structures that demand less. Like we use steel only in most specialized structures like bridges, towers, and so on. And why do we need design? This design of steel structures. So the components individually and the entire structure should withstand load throughout its lifespan, satisfying serviceability criteria. Withstanding a load, as I said, is a collapse criteria, and there are some serviceability criteria on the deflection and sway of the members. To properly design a structure, we have to ensure that it is economical to construct it without compromising safety. So that is one of the most important aspects of design. We have to strike a balance between safety and cost. We cannot compromise the safety, but we cannot keep on making it safer and safer, like using extremely high grade steel material, using like using extremely high grade material, or increasing dimensions extremely to make it very safe, but then it would also become uneconomical. So there has to be a balance, and this balance, once we manage to strike it, that is what is called cost effective design, and this requires the knowledge of the design procedure in detail. Mechanical properties of steel. As a structural material, there are five properties that the Indian standard 800 2007 is the Indian standard code for steel design. 8 IS 800 is the name of the code, and 2007 is its most recent revision. So that is the one we follow. Irrespective of the grade, there are five properties that are taken as constant or standard for all structural steel: the density, the modulus of elasticity or the Young's modulus, the Poisson's ratio, the modulus of rigidity, and the coefficient of thermal expansion. This term is not very relevant in concrete because concrete has a low coefficient of thermal expansion, but in steel we do have to consider it. And these two are the most important mechanical properties of the structural steel that defines its grade. This term grade, they are the yield stress Fy and the tensile or ultimate stress Fu. So that is these two terms we get from the stress strain curve, which we have looked at. And unlike in concrete, where we use rectangular or square sections of dimensions, whatever we feel like giving, in steel, the Bureau of Indian Standards (BIS) publishes an IS handbook number one that has lists of a large number of steel sections of fixed dimensions, and all for example, this I section, this joist, it there are a lot of like ISMB 200, when the D is, this depth is 200, ISMB 250, 300, 350. All these, each of the sections has a designated name based on one of its dimension. For these, it is the, for I sections, it is this depth, and corresponding to each section, they have tabulated all the physical properties. For example, weight per unit length, moment of inertia, the geometric dimensions, of course, that defines it uniquely. It in that handbook, every section is defined uniquely, and several other dimensions and properties, and those are the ones that are ready, processed, like produced in factories, and they are used ready made instead of, unlike what we do in concrete. So these are some of the sections that we have looked at: I section, C section, angle section, and T section. Angle is, today, since we are going to look at design of tensile members, angle section is one of the most commonly used tensile members. So these are the two legs. They can be equal or unequally. Equal legged angles have, this B and D should be equal, and they can also be unequal. And these are some other sections. Flats and plates are also used in tensile, are commonly used tensile members, so we will look at them. And these are some hollow sections, and these are solid sections. This is a stress strain curve of elasticity, the stress strain curve of steel, or the elasticity curve of steel that we have looked at before. When a specimen is made to undergo a tensile test, that is, we increase the load and we keep noting the load. From that, we can calculate the stress, and we measure the elongation. From that, we can get the strain, and we get this stress strain curve: stress plotted on the y-axis and strain on the x-axis. Here it is important to note that normally on x-axis we plot the independent variable. So in a material, though we are applying a force and a strain is developing, here force is not the cause. We apply a force, there is a strain develops in the structure, and as a result the structure develops a resistive stress. So this stress that we are plotting is basically the resistance stress. It does happen to equal the force that we are applying, but it here the strain is always the cause, and the stress is the response, and not the other way around, though it can be a little hard to perceive sometimes. So the point A is the limit of proportionality till which the curve is linear. B is the elastic limit up to which if you remove the stress, the strain entirely goes to zero. Then C and D are the yield points, upper yield point and lower yield point, and the stress corresponding to this is the Fy that defines the grade of steel. We see Fe 250. So Fe, in Fe 250, 250 megapascal is the yield stress of that grade of steel, and E is the uh, ultimate or maximum tensile strength, that is the Fu. So for Fe 250 that we use, generally 410 megapascal is the ultimate tensile stress. So this value corresponding to E will be 410, and F is the fracture point. And in limit state design, we allow we take generally we take Fu, because we will ultimate strength, we do allow it to move beyond the yield point, because we will anyway apply a factor of safety on the capacity. There are these modes of failures: bending, local buckling, shear buckling, web crushing and buckling, and lateral torsion and buckling. Again, as I have said before, buckling is an important mode of failure in steel, because in steel the sections are slender. There is one dimension is much higher compared to the other two dimensions. The two smaller dimensions are the section and the cross sections that we have seen, like these. These are the cross sections, and the dimension going into or out of the plane is the length. So that is generally much higher than these dimensions are barely, if this is 450 400 millimeter, this would probably be something like 50 millimeter or less than that. So these are slender structures, and that is why buckling becomes very important. Design philosophies, we have there are two: working stress method and limit state method. IS 800 2007, the 2007 version follows limit state design mostly, and here the design action has to be less than the design strength. That is the basic principle. The design action is got by the working load or action. We have to multiply it with a factor of safety that is greater than 1, and the design strength is obtained by uh, dividing the actual strength of of the member by a factor of safety, so that both of them are working towards making the design safer. And connections were the first topic we looked at week 3, 4, and 5. They are integral parts of any steel structures. and standard parts are properly have to be properly connected to create steel structures, because as I said, the sections or the members are brought from the factory and then they are assembled at the site. So, and they are not cast together like the way concrete is. So we need to ensure that the members are connected properly so that they are rigid. If rotation is allowed, then it is not a rigid joint. So we have to ensure that if we do allow some joints that are not rigid, that allow rotation but don't allow translation. But if we want to make it a rigid joint, we have to design the connection accordingly. And if we want that it can, okay, the moment is released but the translation has to be stopped. So whatever the whole point of design is that we will put down certain criteria that every part of my structure, I will have certain criteria for every part of it. And every if each part satisfies its own criteria, we will find that the entire structure satisfies the overall criteria that we want, that is to take the overall loads. So because we are working, see, the structure is a big structure. You can't design it all at once, you have to go member wise. So the connections are very important members of of any steel structure. Connection make up a large amount of the cost of structural steel, and connection design should be given top priority for both safety and structural economy. Bolts and wells are the two major types of connections used these days. There used to be one called rivet, but they are not given much importance in IS 800 and they are not used much these days. In week 3, we looked at the design of bolted connections. In week 4, we looked at the design of welded connections. And week 5, we looked at eccentric connections. So today we are moving on to the design of tension members. In a tension member, tension, we know what tension is. Tension is one of the four basic types of forces that we study. There are four types of forces: tension, and compression is included here. Tension is a force along the axis of a member. Bending force is where develops bending moment. Bending moment develops when the force applied is transverse to to the axis of the member. And then there are two, that is shear and there is torsional moment. So torsional moment again has a torsion and tension both have sense or direction along the axis, and bending moment and shear have a direction transverse to the member. So we can imagine that, for example, in concrete design, the most all we were concerned about was bending moment and and shear force. We didn't look at tension or torsion. So in concrete, we had assumed that if the beam is like this, the load will be applied like this, right? This or this. So that is, this is the axis of the beam, and this is transverse. The force applied is transverse to the axis of the beam. So those develop the force corresponding to that is shear, and the moment developing due to that is bending moment. But in steel structures, tension and torsion are all important, and tension members are what we are starting with. So, in a tension member, pulling forces are applied in the opposite directions at the two ends of a member. That is how we perceive basic tension. The bending stresses in the tension member due to its self weight are not taken into consideration. Why? Because they will be negligible. They have That has been studied that it will be negligible. However, in case eccentricity exists in the member due to the fact that the member is not perfectly straight, or there exists eccentricity in the connections that we have studied in last class, we have seen how sometimes the connection is such that the force is applied with an eccentricity, like it is not along the center of gravity of the connections. The force is applied at a certain distance from the center of CG, so there is an eccentricity in the loading or in the connections. Then in that case, either the flexural stresses are considered in design, or the net area of the tension member is modified. Flexural stress means bending stress. Strength of a tension member gets adversely affected due to the presence of nuts, bolts, and pins at connections due to shear lag, reversal of stresses, fractional moment in end connection due to eccentricity, etc. And of course, the most easily perceivable factor is that suppose that we have a plate, where suppose we have two plates and we are pulling at the end of both, and we have to connect them using bolts or rivets. Or suppose we are not considering weld right now, because we don't have to do any drilling. But in bolts, if you put bolts, we have to drill holes, right? So the net area or through which the tension is getting transferred reduces. And what we know is that stress is force by area. In a very crude term, stress is force by area. So if the area becomes lesser, then the stress increases. And the stress is what the stress applied and the stress there is a capacity of the member or what we have to compare, right? So if there is nuts, bolts and pins, since the area of the net area of the tensile member reduces, the stress increases and it becomes, and the strength of the tension member reduces as a result. The present of bolt, rivet, pinholes influence the stress distribution at the section passing through these holes. So generally, we will find that, of course, if you see this section that has no hole and this section that has two holes, obviously the section with holes will have a lesser strength because the area is lesser. So critical tensile strength stress in a tension member occurs at the section where the cross-sectional area is the minimum. As far as possible, bolts, rivets, pins are placed in one line to have minimum reduction in the cross-sectional area of the member. Like one line here means along this. So these are the, see, when the tension is applied in this direction. So the critical sections that we have to consider are perpendicular to the said direction of the tension, right? The tension is applied like this. So this cross section is this plane cross section. If the tension is applied along x axis, then we have to see the look at the cross section on the in the yz axis, in the yz plane. So this here is my yz plane, this dimension, and the one going into the plane. And so we would try to, so that the number of bolt holes along this line is what will make keep on making it more critical. So we would try to get it done by one line of bolts along this, but that is not always possible because connection design, we have already achieved a connection, arrived at a connection design for with other criteria. So suppose there are these, suppose this is the connection arrangement that we have reached. As far as possible, bolts, rivets, pins are placed in one line to have minimum reduction in the cross-sectional area of the member, but often the required length of the connection makes it necessary to provide connection in more than one line, most of the cases. Thus, in this case, the rivets, bolt, pins are placed in a staggered fashion. So this is a staggered, they are placed in a staggered manner, and we'll see later in this class why this helps, why this. So if you have three bolts, putting them like this, there will be greatest reduction in the net area. But if you put one here, and one here, we will see that there is a lesser reduction. So as a result, where the staggered pin bolts are there, the capacity of the section will be greater. Now we look at types of tension members. There are some wires, some called wires and cables. They are used as guy wire in steel stacks, in cable stayed and suspension bridges. This is an example of a cable stayed bridge. The second Hooghly Bridge in Kolkata, for example, a very famous one. These are, you can see that these are called piers. This is the bridge deck. These are piers, and these are the cables. The cables are under tension because there is loading here, and the cables are the one holding up. The loading is in the downward direction, like the gravity induced, all dead load and live load are in the downward direction around gravity. So these, the red marked members are the cables, and they are all under tension, and this pyre is under an overall compression due to this, the Newton's third law of action and reaction. Of course, if there is tension here, this will be under compression, but these cables are tension members and they are generally made of steel. There are another type called rods and bars. They are used in lightly loaded structure like roof trusses. For example, here these are the rods and bars. They are also used to make some structures like gantry girders in steel industries. There is also that is, the gantry girders are used to support and move heavy weight things from one place to another inside the factory. So they are all steel structures, and rods and bars are used there. Then there are flat plates and flat bars that we have looked at. These also have certain, like some the BIS that publishes the standardized sections of IS. These are also included in that, plates and bars. They're predominantly used in footbridges or transmission towers, like these. And rolled sections and built up sections. The rolled sections are the ones that we have, and these are the rolled sections. See, these are called the rolled steel section. The I section, the channel, the angle, and the T, most commonly. And built-up sections, as we have looked at in one of the earlier classes. Suppose you have an I section that is not sufficient to take whatever load we wanted to take. So we put two plates on two sides of this web. Then that will be a built-up section. These plates we have to take from here, flats or plates that have their own stipulations in the BIS, and then we take an existing I section and existing channel section, and we attach one. That attachment will be again through connections. That is another part of connections. Like not just from member to member, but to make one built up section. And these are the hollow sections, these are the solid sections, and these are called the rolled sections. And a roll section combined with another roll section or a hollow or solid section is called a built up section. So built up sections, the advantages of angle section is one of the most commonly used roll sections. So advantage of angle section is that it gives more rigidity to the structure compared to flat bar and do not vibrate under loads. Angle sections are used as lacings in bridges, etc. Bridges we can perceive easy. Lacing is this one special kind of structural arrangement that is used. Suppose these are two columns, these are two steel columns. Lacings are cross members that are attached from one column to another, and they are done to prevent buckling. While we look at design of compression members, a column is a compression member, right? It is very obvious that a column is under compression, just like in concrete designs, in steel design also they are under compression, and they are called the design of compression members. In that we will see that buckling is a very important issue there, not in tension. When a member is under tension it cannot buckle, but when a cylinder member is under compression it can buckle, right? If you can perceive what buckling is, we put for a compression there is a, suppose, okay, there is a column, suppose this is the column, and you put a to compression force, and it does this bending, this kind of bending is called buckling. So we have, so that these lacings prevent the and the buckling has to do with the effective length of the member. So these lacings reduce the effective length, and uh, they are used to, like, they are designed against buckling. So we will look at that, I think, next class. Now we move on to the details and the calculations of the design of tension members. One second. Okay. So the net sectional area of tensile members AN is an important parameter. The net section area of a member is the gross area of the section of the member less, and we have to subtract the area of the holes for rivets or bolt. The gross area of the section is just what we calculate from geometry. There will be a width of the plate and there will be a thickness of the plate. So multiplying that, we will get the gross area, and from that we have to subtract the area of the bolt holes or the rivets, and we will see this is, suppose suppose we want to find the net area in this part. Okay, I'll come one by one. Presence of holes in a member increases the stress at the section due to reduction in the sectional area. That is obviously because stress is force by area. And apart from that, concentration of stresses occurs along the edges of the holes. This is a part of fracture mechanics. There is a course called fracture mechanics in structural engineering. A concentration of stresses is what we are not directly incorporating in design, because as I've said many times, the design is the most straightforward uh, course that we encounter in our undergraduate, because design codes are made and they are laid out in such a way that anyone with just very basic knowledge of civil engineering can follow that. But fracture mechanics comes under structural analysis, so that is a different area that you have to, where we are concerned about the behavior of the stresses, the patterns of the stresses, and they cannot just be laid down as a form, as in a form of steps. Like in design, you will see most design of most members, we have step 1, steps 2, step 3, and then we reach a certain dimension, then we have to check if that is enough. If it is not, we go back to step 1 and again design it. But these concentration of stresses it probably has been incorporated in the code, but you don't have to directly calculate it. Now, AN of flats and plates. Theoretically, a tension member without a bolt hole can take tensile load up to the yield point of the material. This tensile load carrying capacity of the member gets reduced due to the bolt holes. So, take this section ABCD. It has two bolt holes at B and C. So, the plate is provided with bolts along two straight lines called as chain bolting. This is chain bolting. Section ABCD gives the least net sectional area, that is section passing through the bolts. So see, these assuming all these bolt holes are equal, ABCD, this section and this section will have the same net area, and the rest of the plate will have the gross sectional area. If there were, suppose, two bolts in this line, and then there were three bolts in along this line, so this will be the critical one. Wherever there is the maximum number of bolt holes, Here, there all the lines, all the bolt lines have 2 volts, so it is equivalent, all of them. So the net sectional area is the gross sectional area of the plate less the area of bolt holes. 2 bolt holes here. So AN is AG, that is gross area minus area of holes. Now see, area here, it is not this area. This area will be pi by 4 into d square, like the area of a circle, but this is not the area that we are considering. We have to look at the plate from this side. So it is this view. Suppose this is the view of the plate we are seeing. This is the bolt hole. This is the top view, but we have to see it from this side. So if we see from this side, we will see one bolt hole here, one bolt hole here. So this is a diameter and this is another bolt diameter. So this is the overall width of the plate, that is B here. B is the width of the plate. We have to subtract the number of diameters into the bolt holes. So minus N into D, that is the effective width, the total width minus the diameters of minus the diameter of the bolt hole into the number of bolt holes, and then we have to multiply with this thickness, and this is the thickness. So that is what is done here. B minus N D naught into T, where AN is the net section area of the plate, AG is the gross area of the plate, B is the width of the plate, T is thickness of the plate, and we should be very clear about the terms width and thickness. So if this is the plate, this is its width, this is its length. This can go on as long. Mostly you will see length is not in consideration of most calculations. So the length, it can go as long and as along this line. This is the axis of the member. This is the width and this is the thickness. Thickness is usually taken as the smallest dimension. And dn is the number of is the diameter of the bolt hole, and n is the number of bolt holes in the section. Now suppose there are, of course, now you can take this forward, that if there are two holes of different diameters, what will you do? You will subtract b minus the diameter of each bolt. So if there is, this bolt hole has diameter d1 and this is d2, you will take b minus d1 minus d2, and whole you will multiply by the thickness. Okay, and then we look at staggered bolt holes, that I was talking, that staggered bolt holes are done to reduce the, like, to increase the net area. And how is it so? The shows bolting, this 4.4b, this shows bolting in the same two straight lines but in a staggered manner. The deduction of, what is, you understand this, firstly you can understand by intuition that it is staggered. What it means, it is that perpendicular to the application of tension, the bolt holes are staggered, like this. If these lines can be in a straight line, but perpendicular to the tension is applied in this direction. This is the cross section area that we are concerned with. We will see the bolt holes are staggered along this line, this direction. So the deduction of area in this case will be the sum of the sectional areas of all the bolt holes minus, there is this term that is called the reduction on the reduction. So firstly what we do is, yeah. So, firstly, just see it like that. BT is the gross section area. N denote T is the first reduction that we are applying. It is the equal to the area along the cross section due to the bolt holes. And then we do a reduction on the reduction. We, inside bracket, we put this up minus, so it actually adds up in the formula, it adds. So if they were not staggered, this term, I'm coming to this term, but if this term was not present, then the net area would be bt minus n d naught t. But since it is staggered and a term is actually added to the net area, so the net area is greater than what it would be had it not been staggered, and that is working in our favor, right? The lesser the area, the more critical it will become. So we would rather place it in a staggered manner. And this reduction is p square t by 4g for each inclined line between the bolt holes, except the lines in the direction normal to the direction of the applied tensile stress. So if it was along this line, then there would be no reduction on the reduction. These lines are what we are concerned with. This is the pitch. You know what, we already know that this is the what we call the pitch. So the pitch square. This is actually due to, I think this formula actually comes from the hypotenuse or something. So p square into t by 4g, and g is the gauge. So we know that between the distance between the two bolt lines along the tension is called the gauge, and the direction perpendicular to the is called the pitch. So this is pitch and this is gauge. So P square T by 4G for each inclined line. So if we consider this as an example, there are two inclined lines, BC and CD. So you have to subtract this P1 square T by 4G1 and P2 square T by 4G2. This is done. You don't have to take it three times. You have to take each inclined line. Once you have taken this, you have taken the section in a certain, like, basically you have to cut a section through it. Basically what we are doing here, the way we have cut a section perpendicular to the applied tension, here we are cutting a section, but we have to go certain, like, a bit to the left, a bit to the right, to cut the section in an inclined manner. So ABCDE is my section. It has two inclined lines. Do not join B and D again and make it three. Okay, this is not a triangle sort of thing. This is a section that we are trying to cut. So this is the B minus ND naught plus P1 square by 4G1 plus P2 square by 4G2. This will be into T is the net sectional area for the flats and plates with staggered bolt holes. Now we look at angles and T sections. Normally, only one leg of the angle section is connected, and that is called the connected leg, and the other leg is kept free, is called as the outstanding leg. So uh, suppose this is like my column, and I have to attach something, so an angle. So if I attach an angle, the angle is like this. The angle is a is a like, it looks like this. So I have to attach the angle to one leg will be attached, and the one leg will be like sticking out of the column. So this will be this is the outstanding leg, and this is the connected leg. So when load is applied through one leg, then only then non-uniform stress distribution occurs in the angle section because of shear lag effect. We will look at that later. Moreover, eccentric forces produce bending stresses in the sections as well. When all the legs of the section, angles and T sections, are connected, then uh, see, when they're all connected, they will act the same as normal tensile members, like a plate. If all of them are connected, they will act as a plate. But the overall width and gauge length are arrived as shown here. Like, if this, see, if you are looking at a connected leg of an angle, you don't really care whether it is the leg of an angle, or if it is a plate, or it is the web of a T beam, T section. Okay, so then you have to see it in the same way. And I think looking at few examples will make this clearer. But and if the shear lag effect is something we will study in next class, that is a special case for angles and T sections only, because they have an outstanding member sticking out. And there is another term called the net effective area of tension members, ANE. Factors that affect the efficiency of tension members are ductility of the member, shear lag effect, geometric configuration, and method of fabrication. Among all the above factors, shear lag effect is the most prominent one. That is the one we most often comes into the picture. The net effective area of the section is defined as ANE is K1 into K2 into K3 into K4 into AN. This is just I remember that it is similar to these 4Ks. This we also encounter in wind calculation of wind loads in from IS 800 part 2, like 800 part 3. It also, the in the calculation of wind loads also, there were 4 k criteria, k factors. That is not at all similar to, like, it has nothing to do with this one. I just mentioned it because I remembered it. K1 is the ductility factor, K2 is the hole forming factor, K3 geometric factor, and K4 is the shear lag factor. So the various factors are described as below. The ductility factor. As the ductility of the material of tension member increases, the strength of the tension member also increases, since due to high ductility, stress distribution along the bolt holes gets modified, and a more uniform stress distribution the structure can reach a stable state with a stress distribution when the steel is in plastic state. See, this would not have happened if it was a brittle structure. If it was a brittle structure, the moment something goes wrong in one section, it will already fail. There will be no time, there will be no provision of stress redistribution so that the member survives after all. So for ductile materials, it is assumed that there is a uniform stress distribution when the material is loaded beyond its yield point. For commonly available steel with specified minimum ductility, the ductility factor is 1. So generally, mostly you won't be asked questions on this because K1 is taken to be 1. hole forming factor. This is also known as the factor for method of fabrication. In case of bolted connections, the bolt holes are formed either by punching or drilling. In punched holes, the material along the bolt hole gets deformed in shear, and thus the strength of the member gets reduced by about 10 or 15% to that compared to drilled holes. It is assumed that if it is drilled, uh, there is no deformation in shear, by while in punched hole there is some deformation already. That is why the strength gets reduced. This occurs due to strain hardening of the material, which causes loss of ductility. This factor is taken 0.85 for punched holes and 1 for drilled holes. As some of the standards specify, IS 800 2007 recommends to increase the hole diameter by 2 mm while computing the net area of the punched hole rather than using K2 equal to 0.85. And you will see that these, we don't know if they will, whether you do this, like you add to this a n itself. In the formula was b minus n into d naught into t, right? So is 800 says that in that b minus n into d naught, suppose the d naught was 18 millimeter, then you just add 2 to it blindly. You add, make it 20 millimeter, and so the a n as a result reduces, and the ANE as a result will also reduce. So that is one method. And another method is simply putting K2 equal to 0.85 and let AN remain what it was. So both of them have the effect of reducing the net effective area. And why are we reducing it for punched holes? Because for punching, it is observed that there is some sort of deformation in shear along the bolt hole, so the section becomes weaker. So we want to reduce the area. For both of these specifications accomplish the same goal, that they reduce the net area, maybe not by the exact same amount. All of these, now see, all of these are called empirical formula. They are not exact, but these are empirical formula that have been reached at after a lot of research. Now the geometry factor K3, as gauge to diameter ratio G by D of a bolted joint increases, the efficiency of bolted joint decreases. For widely spaced bolt, that is for large gauge distances, like the G will be, these are the bolt lines, right? So if they're very largely spaced, then it is seen that the efficiency of the joint decreases. So for large gauge distances, the metal in between the holes experience non-uniform strain, which leads to local fracture well before the strain gets equalized to the net section. This value of K3 varies from 0.9 to 1.14, but IS 800 2007 recommends this value as unity. So what they're saying is that this is a bolt hole, the bolt line. This is another bolt line. If this increases, then between in this, see, so far if we are taking the area simply as we just simply take the stress as force by net area. Why, when we are doing that, we are assuming that there is a uniform strain distribution along this line. Okay, that we generally always assume, whether we are doing steel or concrete design. We are, no, I think I'm sorry. In concrete design, we did take a strain distribution, parabolic strain distribution. But in steel, here we are assuming a uniform strain distribution. But if the gap between the two bolt lines, that is the gauge, becomes too much higher, then it is seen that along this line between the bolt holes, there is a non-uniform strain distribution, and that leads to local failure. So the value of K3 would be a little less than 1, but IS 800 says it that just take it as 1. And the shear lag factor K4, leaving members like flats and bars, the actual tensile stress in tension member till fracture that occurs at its critical section is less than the claimed tensile strength of the steel, except in the case where all elements of the tension members are arranged that uniform stress distribution occurs over the entire section. This generally does not happen. So for angles and for T sections, there is a shear lag factor that there is a quite a complicated calculation for. We will see that next class when we look at some examples of this topic. Now we look at types of failure in tension members. Now when we have to design a member, we always start with looking at the types of failure, the modes of failure. Then what we do is we calculate the capacity of the section in each of those modes.
Yes, ma'am. Sorry to interrupt.
Yes, yes.
Just had a small query regarding the previous slide,
Okay,
the
okay.
K1 factor, ductility when you talk.
Okay.
Uh, so let's say, so the K1 is considered as 1,
Hmm.
but I mean, I want to compare it with the how ductile the structure is like K1, and if you compare it to the concrete kind of brittle thing, how would be the K1 value?
Pardon again, you are
I
saying that?
mean,
Yes, say.
I'm saying that if K1 is considered for a metal kind of material,
Hmm.
K1 is equal to 1,
Yes.
then what would,
I think your network is a
if the
little.
material is like concrete or wood? Okay.
Yes, I think the K1 will be much much lesser because the ductility. See, the ductility is basically, it means that how in explanatory terms it means how much it can deform because before it actually fails, right? And it is calculated by the area under the stress strain curve. As we looked at the stress strain curve of steel, it was. Can you hear me?
Yes, ma'am, I can
So
hear
the
that.
stress strain curve of steel, it goes like this. So the area inside, you will see that the area inside is very large. Now I'll just show you. Can you see my this thing?
Yes, I can see your Chrome page.
We have looked at this already. Look, the stress strain curve of concrete goes here and it abruptly ends after yielding. Okay, immediately after yielding it fails, while the steel goes like this. The steel goes a lot, so concrete is comparatively a lot more brittle than steel. See, I don't think they can be directly compared by this K1 factor. This K1 factor and all these stipulations that we are studying are applicable only for steel structures. But K1 will be much lesser for concrete and wood. Just if you talk in terms of K1, or if you just see about ductility and brittleness, concrete is way much more brittle than steel.
Uh, just to have the K1, do you have any table for K1 values in it in any textbook or something? I mean, for different kind of, even in the
I
difference of different steel materials.
Okay, yes, that can be possible. I think yes, yes, that's a good point. The different grades of steel, looking at the K1 for the K1 for that is a good, like it is a
Hmm.
good point and it's a relevant point. I think IS 800 should have. Wait, have you looked at IS 800 in this chapter?
No, ma'am. And particular this one I was hearing for the first time, that K1 and K2. I never thought factors are existed actually.
Okay, okay. So if in this is a chapter, chapter 5 is the design of tension members. I'll have to go through this, so you can go through this. If you see that there are these are not mentioned, chapter 5, if these are not mentioned,
Hmm.
it means that K1 has to be taken one irrespective of the grade of steel. But I suppose there will be different factors which may not be mentioned in IS 800, because as I keep saying, IS 800 is a very simplified uh, set of rules that anyone can apply. Anyone with very basic knowledge in civil engineering can apply, but there is a lot of research that goes on behind it. Since so they must have reached the conclusion that whatever be the grade of steel, even if K1 is to be a little lesser, like for point say for 0.95, we are ultimately going to apply the safety factors. They are to account for all these discrepancies, that whatever wherever we have approximated somewhere, the factor of safety cancels them all out and it makes approximations on the safer side ultimately. Okay.
Yes, ma'am. Understood.
It's a good one. I've actually not thought of that. I have to see this. I'll look through this once. Okay. So the failure types of failure in tension members, as I was saying, that whenever we were designing beams in concrete, what we saw that the beam has two major failure modes. In it can fail in bending moment, it can fail in shear. So what we did was we calculated its bending moment capacity, and we had to check that it is lesser than the applied it's greater than the applied bending moment that will come, and we will check its shear capacity and check that it is greater than the shear force that will come. So similarly for tension members, there are three modes of failure: yielding of gross section, rupture or fraction or fracture of net section. Yielding and rupture are two different things. Like yielding has to do with the Fy, and rupture is fracture, so it has to do with the Fu, when the final section actually breaks. And block shear failure. So yielding of gross section TDG, we will actually see another important thing, like the example that I gave with concrete was that bending moment and shear force are two different forces. So we would check both to both those two. Or we could do another thing is that we would check the bending stress, we would check the bending stress coming on the structure, we would check the yield, the shear stress coming on the structure, and we have to, and the strength of the structure will be the lesser of the two. So for this also, all these three, yielding the rupture and block shear failure, for all these we will come up with a stress sorry, a strength of the structure. This section will have a certain strength in yielding, it will have a certain strength in rupture of net section, and it will have a certain strength in block shear failure. So there will be three values: TDB, TDN, and TDG, and the minimum of the three will be the capacity of the section, because what does capacity mean? That is the maximum it can withstand without failing. So we have to take the minimum of all of the strength corresponding to all the modes of failure. Here there are three. So in this type of failure, where the yielding of the gross section occurs, a significant amount of deformation occurs before the material actually gets fractured. This deformation makes the structure unserviceable. I think we have had a discussion about why in like in bolts, why in welds. I think why we were taking the ultimate stress somewhere, and the tensile and the yield strength somewhere. That is when we take the yield strength only when there is so much deformation that the structure becomes unserviceable and it cannot serve the purpose that it is been designed for. A common example that always comes to my mind is that, suppose in a factory, in a steel factory, you have a beam on near the ceiling, that is that at the door, suppose the lintel beam. So if it bends a certain amount, or if it deflects a certain amount, then you can see, you may find that some instrument cannot be passed through it anymore, because you need a headroom for like the moving the instrument from one place to another, suppose that, then it becomes unserviceable. Even if the beam is still holding, even if the structure has not failed at all, like not collapsed at all, it cannot satisfy the purpose for it it was built, so it is unserviceable, so it is as good as failing for us. So though the collapse limit state is more critical, in the sense it has to do with, like, it can lead to loss of life or loss of property, that is in a way more critical, but we have to design for both the collapse limit state and the serviceability limit state, because we have built the structure for a purpose, and we want that the structure should satisfy that purpose as well till the end of its life. So this is in yielding of gross section, it becomes critical when the section is yielded so much that the deformation makes the structure unserviceable. Now the next is a rupture of net section or fracture. This is clearly, the this deformation is occurring in the net section, so the holes are somewhere else. Maybe this section is a gross section, this can yield, but the net section will fracture. So when the net section of a member reaches the ultimate stress, this is the FU, then rupture or fracture of member takes place. But again, just remember that all these formula that we are applying, we will anyway apply a factor of safety in the denominator. So we would never, even in our design, at the most critical point, that is when load is equal to when capacity is equal to applied load, we are not actually letting the member reach the ultimate stress, okay, because below that FU, there will be a factor of 1.1 or 1.25 reduce, bringing it down so that it is safe. Even at the critical point, it is safe. When the net section of the member reaches ultimate strength, then rupture or fracture of the member takes place. This is called rupture of net section, and this is block shear failure. This is a interesting and little difficult to perceive. What happens here is this: see, the a segment of the block of the material or the concrete of the connection shears out. So what is happening is you are applying tension. So this section is not failing, that means that the place that a plate is itself is not failing, the bolts are not failing, but this entire region that is like outlining the bolts, it's just shearing out. So this, when you are applying a tension, if that happens due to possibly high bearing strength of steel and high strength of bolts. If the steel and bolts are too strong, there is another formula that all of these will have corresponding formulas, but this entire section shears out. See, the plate here is intact, the bolts are intact, everything is intact, but along this line as a whole, it shears out. This is called block shear failure. So the design of tension members, the design of tension member is based on two limit state based on yield strength of member due to its large elongation, and limit state based on the ultimate strength of the member. This limit state is particularly crucial where the section of the tension member gets reduced due to the presence of bolt holes. So this is the again this is the serviceability limit state A, and B is the collapse limit state. A tension member with bolt holes at the ends for connection purposes, even if subjected to tensile stresses in excess of yield stress to as high as ultimate stress, the member may not elongate excessively because of the presence of the so-called non-active metal behind the bolt holes in the direction of the tensile force. Just at the point of fracture, the metal tends to narrow out at that point where the fracture occurs, but the additional metal present behind the bolt hole, this additional metal, by this we mean this part, because here this part is missing, but just behind it this part is a solid section, right? The metal tends to narrow out at that point where the fracture occurs, but the additional metal present behind the bolt hole restricts this contraction of the strained metal, thereby increasing the ultimate strength. Thus, fracture at the next section passing through the bolt is considered another limit state. The design strength of a tension member is the minimum of the following: design strength due to yielding of the gross section (TDG), rupture of strength of critical section, there is a net section. This will be the ones with the bolt holes. The A is without bolt hole, B is with bolt hole (TDN), and the block shear strength (TD). I think TDB. So the design strength of the member will be the minimum of these three, and in all these three, a factor of safety will automatically be incorporated in the formula. So next class we will look at some examples of design of tension members, and we'll also see how the shear lag factor works. Okay, so are there any questions?
Yes, ma'am. I do have a small thing.
Yes.
So yeah, this is related to the previous uh, work session.
Okay.
So like we are having the eccentric loadings perpendicular to the plane of
Yes.
bolts or parallel to it. So so mostly we come across shear and bearing or shear and moment and tension and like combinations of things. So when we exactly like coming to the end of the problem, we will be the combination of two. We usually go for shear square plus bearing
Yes.
square plus. So that
I think your
right
net.
one combination. So
I have to say again, your connection went off for a while. Repeat it again.
okay,
Shear square plus bending square. That ratio has to be less than one. That is what we is a criteria.
I mean yes, in that last situations, there are two to three formulas. Like in one case, we are going through what you said. In other case, we have the resultant kind of thing, and that resultant is compared to uh, the factor load. In the other case, we have a square plus three q square under root of this thing. So there are two to three different combinations. So when
Okay, when to use
this
which
should be
one?
applied and all. Yes,
Okay, okay.
but did you get my point
I
right now?
got your point that there are two to three
Yeah.
formulas. Which one should be used when?
Hmm.
Wait, I'll see. Where eccentric connections. You can see my screen, right? Do you know where eccentric connections are in the code?
Okay, in the
Maybe in the appendix connections. Or everything in the code is mentioned very clearly, like which one has to be used when. So I'll check once.
okay.
The code, that is what it actually does. It shows every, like if you are working within the code, whatever any book says, you are right if you are following the code.
Mhm.
So I'll just see if the code has something to say on that.
This is one
This,
of the
but
thing, I guess.
this is one of the where bearing stress if there is converted bending, okay, one more sulfur converted.
This is for both, I guess. The left side to it is like combination of two forces, Fa
Yes.
and Q, and the right side is like three forces, combination of three forces. This is
Yes.
only for bolting. This is kind of straightforward, I guess, in particular kind of bolting.
Yes. Then
Uh, hmm. But in particularly when calculating for eccentric loadings,
hmm.
we are coming across two kinds of load. That two things are little different for when we consider for if the load is perpendicular to the plane of joint and
Okay.
different for
I
parallel.
think I think in eccentric loads we always use the resultant, right? Have you seen this formula being used in, because in eccentric loading it comes like geometry. Have you ever seen this
Mm,
being used for eccentric joint, eccentric connection?
this one, ma'am, while we are considering eccentric loading where it is perpendicular to the plane of joint,
Okay, well
because
then,
we will get tension and shear.
yes, 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 right, right. Okay, so I'll check this and let you know next class. I'll have to read up a
Sure,
bit
ma'am.
about this and go through the code.
Sure.
Okay, I'll write it down. Okay.
Okay, ma'am. Then, yeah.
Any more doubts?
Nothing, ma'am. Nothing else.
Okay, okay, fine. Then we'll meet next class. Look at examples of tensile tension members.
Sure, ma'am.
Okay.
Right.
I end the class then. Thank you for attending.